So go ahead and read the first one. And you'll notice the wording is very similar for all of them. They're not going to be too different from one another. Okay. So we're buying Easter egg goodies, right? And we're going to make at least 6 baskets, right? And the bunnies cost $4, and the Cadbury cream eggs cost $3 each. And we want to spend at most $36. So let's begin with these two phrases because that's actually very important. What does at least and at most mean? Okay. So let's look at that carefully so we don't make any mistakes from here on out. So at least. So if you want at least $20, is that $20 or more or $20 or less? If you want at least $20?
So we're in a budget?
Yeah, they want at least, I'm just saying, it's a fictitious number, but if you ask for at least $20 from somebody, are you asking for $20 or more or $20 or less?
Yeah.
$20 more.
$20 or more. If you said, I want at least $20, you don't want 15, you want 20, 25, something bigger, right? So the word at least means greater than or equal. If you look at the context. Now, if some of you just look at the word, oh, least, that's pretty much the same as less, so it means less than, and you're just making it up with no, application, that could get you in trouble. Same thing at most. If you want at most 2 hours of homework, would that be 2 hours or more or 2 hours or less? 2 hours or less. If you want at most 2 hours means less than or equal to. So you notice how the wording doesn't necessarily match the inequality sign and the meaning. The wording and the meaning do not match. So don't just go off of, least, less than 6, and you're just kind of, replacing words with symbols that don't necessarily match with each other. So we got to keep this in mind as we're doing this. Otherwise, all our shading will be wrong on every single problem we do. If we use this word, at least and at most, you'll see that repeatedly. It's like, at most we want to spend $40. At least we want 5 arrangements of flowers. So you'll see that repeatedly on all these questions, so we have to know that from the beginning so we don't do that wrong. All right, so from there, we want to get some variables going. We have an x and a y, right? But really, we have chocolate bunnies, and we got these Cadbury cream eggs. So we generally like to use like a letter that it stands for. So when we're talking about the problem, when we say B equals, we know we're talking about the chocolate bunnies and the Cadbury cream eggs. We know we're talking about the, C. So, but they can be thought of as like B is going to be like our X and C is going to be like our Y. So we're going to have to solve for Y to graph it. Just know it's going to be the letter C instead of the letter Y. But it's the same steps that we've already done. And then when we go to graph it, okay, I'm going to make sure I put the labels correctly. So since these are going to be like my Y, I'm going to put that here. And down on my x-axis, I'm going to put the chocolate bunny. Right down there. And this is now, if you actually switch these and you say, I want to put the bunnies on the y-axis and flip-flop them, that would be correct too. There's not a right or wrong here. So you might have a different graph than somebody else in the end if you just happen to choose this for x and this for the y-axis. It doesn't necessarily mean it's wrong. As long as you get the correct answers at the end, which I'll show you, it's fine. Alright, so let's write a system of inequalities. So they don't just tell us, here's what the inequalities are, we have to come up with them. So we know we need to make at least 6 baskets. So we know it has to be greater than or equal to 6. At least means greater than 6. Well, what has to be greater than or equal to 6? The number of bunnies plus the number of the cream eggs. So we're going to say our B plus the C, right? The number of how many each of we're going to get has to be more than 6. Or 6 exactly. And then we know since the bunnies cost $4, 4 times the number we get, that's how much the bunnies cost, chocolate bunnies, plus $3, right? $3 each for the Cadbury, so $3 a piece. That has to cost less, or at most, $36. So for each of the problems, you're going to have to come up with the two inequalities that make up the system. Remember, system? That just means there's two of them, or two or more. All of ours just have two. That's what they mean by system. And we need to solve these, graph these, find the slope, find the y-intercept, see where the shading overlaps, just like we have there. So remember, my C is kind of like the y. So I want to get C by itself. So you're going to do the same old steps, right? Subtract b on both sides, and you'll have c is greater than negative b plus 6. Same steps we've always done. You can think of this negative b as negative 1 over 1 slope. And then we need to solve this one for c, which is the same as y. So we're going to subtract 4b. So a lot of this will be familiar. You know how to do this. It might be look a little different because we're having different variables instead of x and y. Now, if it really bothers you, you can just use x and y. Do x plus y is greater than 6, and so on. Plus 36. And this one, we have to divide by 3. C. Don't need to flip the sign because we divided by a positive. And 36 divided by 3 is 12. So that would be the first steps, coming up with inequalities, and then you have to solve them for a variable. That's going to be like your y variable. Alright, so we have to graph them. Notice how there's no numbers here. Because if it's really big numbers, we might have to count by like hundreds, or 50s, or 20s, or 5s. We don't necessarily have to count by ones on everything. So looking at this, what should we count by? Okay. Can we count by 1? Knowing our y-intercept is 6 and 12. Can we count by 1s here? Does that work? So let's take a look. If we count by 1s, we'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we can't even get up to 12 on the y-axis, so we should probably count by maybe 2s. Yeah, so you have to figure out each problem what to count by. So this one, we'll count by 2s. And the next problem, we might count by 3s or 5s or 1s or, who knows. But you just have to figure out each problem. And since my slope, you see it's going to be over 1 and over 3. That's kind of a hint that I want to count by 1s because I want to be able to get to 1, 3, 1, 2, 3, 4. I need to be able to get to each and every one of those. So I'm going to count by 1s, and hopefully it all fits. Sometimes you'll do all this work and graph it, and then your graph goes straight off and never intersects because the numbers are too small or too big. So you just have to take a chance. Maybe you have to redo it. Smaller so it fits. Alright. So here we go. Let's graph this other one right here. Let's start at 12. Put a dot there. And I'm going to go down 4 and right 3. Now that doesn't mean down 4 squares, right? If I'm going to go down 4 from 12, I'm at 8. So down 4 is actually only 2 squares since we're counted by 2. So down 4, and we're going to go to the right 3. See, I'm counting by 1s on the left and right, so that's why I'm 3 squares here. And I just repeat that a few times until I end up hitting that x-axis. I finish it. So I'm going to go down 4 again, which is 2 squares over 3. And down 4 again over 3 squares. There we go. Now I'm not going to connect these, by the way. I'm just going to leave them as dots. I'll explain why in a little bit. And then do the same thing for our other one. We're going to start at 6, it was. Yeah, start at 6. and I'm going down 1 over 1. So that's really 1, down 1 over 1 is right here. Down 1 over 1, so on. I hit the bottom. Now, the shading. I want to shade everything less than the red, everything below the red, that's all of this. All this is less than the red. But I also want to shade everything above, greater than the blue. That's all of this. And your answer is where they overlap. That's beautiful. So you can see it's right in between the two. That's the answer. So erase everything except for what's in between. Shade it in, not too dark. Still want to be able to see where all the lines cross inside. Okay, so this is kind of where we stopped last time. Right? We just said, okay, we graphed it, we're done. Well, here's where the kind of real world stuff kind of kicks in. And what can you use this for? So what do all these points actually mean that are shaded? So if I look at all these that are inside, what do those actually mean? We're saying that these are answers, but answers to what? What do you guys think? Yeah? What are these answers to?
They're the same right there.
What do you mean the same?
They all cost the same.
They all cost the same? Close. Remember, our restriction for cost is they just have to be less than $36.
Oh, okay.
So, yeah, so these are all in the budget, but what else is true? Yeah?
All possible combinations.
Okay, that are below $36, but also that are more than 6 different pieces, right? So it's both of them. So if you look at any of them, go ahead and pick one. You can check to see if it's true. Let's see here. So if I just pick, let's say here, 5. Yeah, let's do this one. That's the next question. It says, go ahead and what are one of the possible combinations here? Let's do 5 chocolate bunnies. All right? And 4 of the cream eggs. So that would be 5, 4. X, Y, or in this case, C, or no, B, C. B, C. All right, what does that mean? Okay, so 5. And 4. Now these solutions are actually standing for mean something. And then they ask, well, check your answer. How do you know this is an answer? Not by looking at the graph. Well, that's when we go back to your inequalities. Go ahead and rewrite both of them, the original ones. All right, let's rewrite this one and this one down below. And then we'll plug it in and check it. So we know that B plus C needs to be greater than or equal to 6 of them. But then, I think it was 4B plus 3C, $4 for each of these, plus $3 for each of these, needs to cost less than $36. So let's verify that with 5 and 4. Now you can pick any point that's in the shaded region and it'll work. That's why it's in the shaded region, is because they're all bigger than 6, right? So we can try here, 5 plus 4. You know, you just verify algebraically. Oh yeah, 9. 9's bigger than 6, so that's good. That checks out. That's a true statement. And then you're going over here and plugging in 5 and 4 and making sure that it all costs less than $36. So when you plug in the 5 bunnies and 4 eggs and you calculate how much they would actually cost, you get $20 plus $12, right? And 20 plus 12 is 32, which is definitely less than $36, which you don't really need to worry about if it's going to be true or not, because that's why it's in the shaded region. As long as you graphed properly up here, I could have picked any one of these. I could have picked this one, like 1 chocolate bunny, 8 eggs. It would still be more than 6 and less than 36. That's what all these have in common. So if your boss one day says, like, I want all the possibilities that give me this, and you know there's a ton of different possibilities, this is how you'd figure out what they are. By the way, how many different possibilities are there? You can count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28 different possibilities. Right? And you can figure out how much they all cost. Now, if you actually found out how much they all cost that are exactly $36 and exactly, you would have you can actually see those on straight lines. There'd be fewer choices, but that's possible as well. Okay. All right, so that's one of them. That's just one problem. Okay, I did a lot of explaining all this, but we can do another one. If you think you got it, you can try it on your own. But I'll do one more, and then you guys will try to finish the next 2 on your own by the end of this period. Okay? So let's try this one. I'm going to go a little bit faster, more real time. Okay? Still pick out these key words. So right here, we have at least, right? So what symbol is at least? Right? Don't forget that's greater than or equal to. And over here it says it's going to cost at most $40. So that's going to be less than equal to $40. So we're buying flowers this time. So I'm going to use D for daisies, which will be like my X variable. I'm going to use R for roses, which will be like my Y variable. So my graph, I want you to put that on there right away so I don't accidentally mix them up later. So roses will be for Y. Daisies, D-A-I-S-I-E-S, be here. Right. And now let's write a system of inequalities. So it's going to be very similar. Before we had to have at least 6 different chocolates. This one is like at least 5 different arrangements. So it's very similar. So we know that D plus R just needs to be 5 or bigger. Right? Greater than or equal to 5. It's the same thing as 5 or bigger. And we know that the daisies cost $4, so 4 times each daisy, how much the daisies cost altogether, plus $8, how much each of the rose bouquets cost together. And those add together, the cost of the daisies and the cost of the roses, all has to be less than $40. You only have $40 going in there, so it has to be $40 exactly or less. Right? And much like before, think of the R as the Y variable, so we need to solve for R of both of these. So start by subtracting D on both sides, and you'll see a lot of similarities with the one we just did. All right, so go ahead and do that for both, and then decide what you should be counting by on your graph after you solve them. So last time we counted by 2s to get up to 12, to be able to graph 12, because this only goes up to 10 total. So look at what your y-intercepts are and decide, well, what should you start on here? Should you count by 1s or something else? Go ahead and do that now. Solve both of these for R just like we did before and start your graph. Okay, so I see that most of you have the R, R greater than negative D plus 5. Right, then you solve this one. And you have this one, right? D plus 40. divided everything by 8. Right? R less than or equal to negative 4 over 8 is negative 1/2. You can reduce that. And 40 divided by 8 is 5. So here's where you evaluate what you should count by. Some of you were looking at 40 and you just started counting up to 40, but we don't need to graph 40. We need to graph starting at 5. And it's the same for both. Both of them have the same y-intercept. So you decide on the scale after you have solved and you're ready to graph. So if we don't need to count up to 5, then we're pretty safe counting by ones, because we'll get to 5 pretty quick. But this will change from problem to problem. This depends on how much it is, whatever it is you're buying. Smaller, I fit it. So, let's do this one in black. I'm going to start at 5. And I'm going to go, same thing, down 1, right 1. Down 1, right 1. This time we're counting by 1, so it's actually going to be down 1 square, right 1 square, and so on. And then we can do the next one, we'll do this one in blue. Start at 5 again, but this one's down 1, right 2. Down 1, right 2. And repeat that. Now, once again, notice how I am not going to connect the dots. I'm not connecting the dots here. So let me explain that real fast before we move on. Now, what do these dots actually stand for? They're standing for different flowers. But what does it mean if you start doing points in between all these? Okay?
Thank you.
Right. What does that mean? All those points in between, what do those mean?
Those are all the.
Well, yeah, but we're talking about flowers, right? So this is like 2.3, right? And this is like 3.7. Can you have 2.3 daisies and 3.7 roses? No, right? So that is why I'm not connecting these at all. The only real true answers. The only real true answers are these whole numbers, because you can't buy a fraction of a bouquet. You have to buy the whole thing. Okay? So that's worth noting, so you should not have these connected. Okay? Furthermore, when you do the shading technically is not everything inside. It's not all of this. Gotta go. And it's not technically all of this, but just the whole number answers that are inside here. Okay? So this could be an answer, this could be an answer, this is an answer, but nothing really inside, all this other empty space, because you can't buy fractions. But anything in the shaded region, these are all the possible answers. So there's a limited amount of how many there are. It's not like there's an infinite amount, because we don't have all the fractions. We can actually count how many possible answers there are just by counting up all these dots. That should be shaded a little bit more down there. That's shaded as well. There we go. Okay, so none of your answers should be connected because you cannot have fractions for answers here. So pick one possibility. Pick any of these and go ahead and show the work. Remember, take the original equations, d plus r, and plug them in. So you have d plus r must be greater than or equal to 5. Right, that was one of them. And then the other one was 4d plus 8r must be less than $40. $4 per daisy plus $8 for rose must be less than $40. Okay? So whatever you get for your answer here, right, for your number of daisies and roses. You're going to plug it in here and show that it's true. So on the last one, we just had to show, yeah, 9 was bigger than 6, so that's true. That works. $32 is less than the $36 we were budgeted for, so that's true. You're showing both of them are a true statement. Okay, so if you have any clarifications, you need anything clarified, go to the example on the other side and you can see how it should look. Alright, I'll let you do that, and I'll come around and be checking that right now.